Spring 1927, Highland Park, Michigan. At Chrysler's engineering facility, Chief Engineer Carl Breer examined yet another defective clutch assembly from the Chrysler 70 sedan. The issue was frustratingly straightforward. Engine oil was infiltrating the clutch mechanism, causing slippage. Customers reported their vehicles jerked and stuttered. The clutch pilot bearing, a bronze sleeve bushing installed in the flywheel, was designed to center the transmission shaft. However, its position, deeply embedded between the engine and transmission, rendered it virtually inaccessible for maintenance. External lubrication was impossible, and servicing required disassembling nearly half the powertrain. Breer experimented with every solution imaginable. Enhanced seals still leaked. Grease-packed bearings attracted additional oil, and graphite bronze bearings wore out prematurely. Nothing solved the problem. This challenge persisted throughout 1927 and into 1928. Then Breer conceived what seemed like a ridiculous idea. What if a bearing could store its own oil supply internally? Essentially, a metallic sponge saturated with lubricant. This concept was considered impossible. General Motors had attempted creating bearings from compressed copper and graphite powder in the early 1920s and failed. The bearings either disintegrated or couldn't retain the oil. The idea was dismissed as impractical. But Carl Breer was persistent. He brought in two specialists, mechanical engineer William Sherwood and metallurgist Bill Calkins. Their mission: make the impossible bearing functional. By 1930, they succeeded. The invention, named Oilite, would transform the bearing industry globally. More significantly, when World War II erupted and American tanks began overheating in North African deserts due to inadequate lubrication, Oilite bearings provided the solution that kept armored vehicles operational when conventional bearings failed. This is the verified account of how Chrysler engineers converted copper powder and vacuum technology into self-lubricating metal, developing a technology so successful it remains in production today, nearly a century later. Cham's technical background. The Chrysler 70, also designated B70, introduced in 1924, represented Walter Chrysler's debut automobile under his own brand, a six-cylinder vehicle positioned to compete with Ford and GM. Sales were strong enough to establish Chrysler Corporation as a legitimate automaker. However, by 1927, warranty claims were accumulating. The clutch issues weren't catastrophic. Vehicles didn't fail completely, but the problems were troublesome. Drivers reported erratic engagement, slippage under load, and accelerated wear. Breer identified the culprit: the pilot bearing, a small cylindrical bronze bushing supporting the transmission input shaft tip, where it connects to the engine flywheel. This bearing operated under hostile conditions. No external lubrication access. Location buried between engine and transmission. Constant oil contamination from leaking seals. Heavy loads from shaft weight and clutch engagement forces. Difficult access, requiring transmission removal. Conventional solutions failed. Greased bearings attracted oil, causing clutch slip. Dry graphite bearings wore rapidly, and oil bath systems were impossible due to lack of sealed chambers. Breer needed a bearing with its own permanent oil reservoir, protected from external contamination yet releasing lubricant only when friction heated during operation. Such a bearing didn't exist, so Breer decided to invent it. Carl Breer recruited William Sherwood and Bill Calkins specifically for this project. Sherwood brought expertise in mechanical engineering and manufacturing, while Calkins contributed metallurgical knowledge about metal behavior at varying temperatures and alloy formation. They began with established technology, powder metallurgy, the process of forming components from metal powders. This wasn't revolutionary. Industries had used metal powders for years to manufacture parts difficult to machine or cast. The basic process involved 1. Mixing metal powders, typically copper, tin, graphite. 2. Pressing in molds under high pressure to form shapes. 3. Sintering in furnaces at high temperatures below melting point to fuse particles. The result: solid metal components without casting or machining. General Motors had attempted adding graphite to copper tin powder to create self-lubricating bearings in the early 1920s. The graphite, naturally slippery like pencil lead, was intended to provide lubrication, but the bearings failed. Either too porous, too weak, or the graphite couldn't provide sufficient lubrication under high loads. Sherwood and Calkins adopted a different strategy. Rather than relying on solid graphite for lubrication, they would create porous metal capable of holding liquid oil internally. Their key innovations included controlled porosity. By carefully selecting particle size and sintering temperature, they produced metal with interconnected pores throughout, like a rigid metallic sponge. Oil impregnation. They placed sintered bearings in a vacuum chamber, evacuated all air, then flooded the chamber with oil and restored atmospheric pressure. The pressure differential forced oil deep into every pore. Capillary action. The microscopic pores functioned as capillaries. When friction heated the bearing, thermal expansion pushed oil to the surface. Upon cooling, capillary action drew oil back into the pores. By 1929, Sherwood and Calkins had functional prototypes. The bearings retained 25 to 30% oil by volume. Approximately one-third of the total bearing volume was oil stored in pores. When wiped clean, they appeared completely dry, yet under friction and heat, oil emerged at the bearing surface, providing lubrication precisely when and where needed. Sherwood filed patent applications in 1929 and 1930 through his patent holding company. The patents detailed the vacuum impregnation process, evacuating air, submerging in oil, and pressurizing to force oil into pores. The first oilite bearings appeared in 1932 Chrysler automobiles, specifically in the floating power system. Chrysler's innovative engine mounting that reduced vibration. The bearings perfectly resolved Breer's original clutch problem. Installed in the pilot bearing location, they provided continuous lubrication without external maintenance. The oil trapped in porous bronze couldn't escape to contaminate the clutch, yet friction heat brought it to the bearing surface during operation. But oilite's applications rapidly expanded beyond clutches. Water pump bearings in hot-wet environments. Leaf spring shackles eliminated persistent squeaking. Starter motor bushings, high-load intermittent operation. Generator bearings, continuous rotation with limited maintenance access. Distributor shafts, precision applications requiring consistent lubrication. Sales skyrocketed. Chrysler reported selling 7 million oilite bearings in 1932, during the depths of the Great Depression. By 1933, sales reached 18 million. Oilite became a profit center for Chrysler, during years when automobile sales were collapsing. Walter Chrysler approved establishing the Amplex Corporation and its Oilite division to manufacture and market these bearings. The division rapidly branched out from automotive uses into industrial machinery, marine propulsion systems, and aviation. By 1935, Amplex operated from a massive 9-story facility covering 5 acres at 6501 Harper Avenue in Detroit, with approximately 200,000 square feet of production space. The plant manufactured not only oilite bearings, but an increasingly diverse portfolio of sintered metal products, gears, structural components, and filters. Another breakthrough emerged from Carl Breer's problem-solving approach. During the 1930s, gasoline contained sediment and contaminants. Fuel tanks employed glass sediment bowls with wire mesh screens to prevent debris from entering carburetors. However, wire mesh was costly and couldn't filter finer particles. Breer proposed manufacturing filters from sintered metal, using the same porous structure as oilite bearings but without oil saturation. The pores would capture sediment while allowing fuel to pass through. Early trials were unsuccessful. Engineers attempted creating perforated steel strips, but couldn't achieve uniform pore dimensions. Then they discovered the solution. Using powder with consistent particle size, sintering it flat, produced filters with regular pore structure. The sintered metal fuel filter proved remarkably effective. It could even separate water from gasoline. Breer described a famous demonstration. One of our executives experienced fuel depletion in a rural area. He stopped at a farmhouse and requested a small bucket of water. The farmer obligingly provided it and watched in amazement as our executive poured water into the fuel tank. To the farmer's shock, our executive engaged the starter and drove away. The reality was that our new filter was so efficient, it allowed gasoline through while blocking water. When water was added to the tank, it raised the small remaining gasoline to where the filter could pass it, sufficient to reach the nearest service station. The Army evaluated numerous fuel filters for military vehicles in the late 1930s. Amplex's sintered metal filter was the sole design meeting their specifications. It became standard equipment on military vehicles through the 1950s, eliminating glass sediment bowls that could break under combat conditions. World War II application. When Germany invaded Poland in September 1939, European powers urgently sought American military production. Britain and France ordered substantial quantities of trucks, aircraft, and armored vehicles to augment their overtaxed industrial capabilities. Simultaneously, the U.S. Army underwent rapid expansion and modernization, preparing for potential conflict involvement. New armored designs were being assessed, including the M2 medium tank and early prototypes. that would eventually develop into the M3 Lee Grant and the M4 Sherman. Field testing, especially in hot, dusty climates, revealed numerous maintenance and reliability issues. Tanks proved to be mechanically demanding machines, with operating conditions that stressed every moving component to its maximum capacity. Armored vehicles encountered particularly challenging operating environments. Extreme heat, interior temperatures inside armored hulls could surpass 140 degrees Fahrenheit, 60 degrees Celsius, causing rapid lubricant degradation. Dust and sand. Microscopic abrasive particles infiltrated seals and enclosures, contaminating lubricants. Continuous vibration, tracks, rough terrain, and weapons firing subjected mechanical assemblies to constant shock loading. Restricted maintenance access. Many components were deeply embedded within suspension systems, drivetrains, or turrets, making frequent field servicing challenging. Traditional lubrication methods struggled in these conditions. Grease-packed components collected dust, creating abrasive mixtures that accelerated deterioration. Oil-lubricated parts needed regular inspection and replenishment, often impossible during extended operations or training exercises. British forces deployed in North Africa from 1940 onward faced identical challenges. Their tanks, including the Matilda II, Crusader, and Valentine, demanded intensive maintenance schedules to remain functional in desert environments. Dust infiltration and heat increased wear rates across numerous mechanical systems, placing severe demands on crews and maintenance personnel. American armored units training in desert regions, including Yuma Proving Ground in Arizona, observed similar patterns. Early U.S. tanks demonstrated that prolonged desert operations substantially increased mechanical wear and maintenance needs. The Army Ordnance Department investigated multiple approaches to enhance reliability, improved sealing techniques, modified lubrication procedures, and material enhancements. While no single solution eliminated all issues, the experience emphasized the importance of components capable of reliable operation with minimal external lubrication and reduced maintenance dependency. Concurrently, self-lubricating sintered metal bearings, like Chrysler's Oilite bushings, already in civilian and industrial use since the early 1930s, gained increasing recognition across industry and military manufacturing as an effective solution for applications where regular servicing was difficult or impractical. Military testing and deployment. The Army Ordnance Department contacted Amplex in 1940, requesting Oilite bearing samples for military evaluation. Could they endure tank operating conditions? The answer was overwhelmingly affirmative. Oilite bearings resolved every desert-related problem. Self-contained lubrication. Oil trapped within pores couldn't leak and couldn't be contaminated by external dust. Heat tolerance. Bronze tin alloy maintained stability at temperatures that degraded conventional greases. Dust immunity. Bearing surfaces remained clean. No grease to attract and retain abrasive particles. Extended service life. Bearings operated thousands of hours without maintenance or replacement. Access independence. Since bearings required no servicing, inaccessible locations became irrelevant. Testing at Aberdeen Proving Ground validated these advantages. Tanks equipped with Oilite bearings in suspension, transmission, and turret mechanisms operated in simulated desert conditions for thousands of hours without bearing failures. Production contracts followed immediately. Amplex dramatically expanded manufacturing capacity to satisfy military requirements. By 1942, the Oilite division was producing bearings for tanks, complete suspension and drivetrain systems, aircraft, Supermarine Spitfire, P-47 Thunderbolt, B-17 Flying Fortress, naval vessels, propeller shaft bearings, steering mechanisms, gun turrets, military vehicles, trucks, jeeps, half-tracks, any vehicle operating in harsh environments, industrial equipment, factory machinery, supporting war production. Amplex's wartime production figures were remarkable. The company eliminated hundreds of thousands of machinist hours during the war, producing high-precision sintered products without material waste. Sherman tank application. According to company documentation, the M4 Sherman tank, America's principal medium tank during World War II, utilized Oilite bearings extensively throughout its vertical volute spring suspension, VVSS. Each Sherman contained 6 bogie assemblies per side, 12 total, each incorporating multiple bearings, bogie arm, pivot bearings, suspension arms attached to the hull, road wheel bearings, supporting twin road wheels on each bogie, track roller bearings, supporting return rollers for the track. Conventional bearings in these positions required frequent lubrication through grease fittings exposed to mud, dust, and water. In desert or muddy conditions, contamination destroyed bearings within days. Oilite bearings eliminated this maintenance burden. Sherman suspensions could operate for weeks without servicing. When British forces received American-built Shermans for the North African campaign in 1942, maintenance crews were astonished by the reduced bearing maintenance compared to British-manufactured tanks. General George S. Patton's Third Army, racing across France in summer 1944, pushed Shermans to their mechanical extremes. Tanks operating continuously for weeks maintained functional suspension bearings, thanks to Oilite's self-lubrication capability. Manufacturing process. The engineering behind Oilite was elegantly straightforward, but demanded precise manufacturing. Material composition: 90% copper, 10% tin, less than 1% iron, trace amounts. Sometimes graphite for enhanced lubrication properties. Manufacturing steps: 1. Powder preparation. Metal powders ground to precise particle size, typically 150 to 200 mesh. 2. Blending, copper, tin, and additives thoroughly mixed for uniform composition. 3. Pressing. Powder compressed in steel dies under 20 to 50 tons per square inch, forming green compacts. 4. Sintering. Heated in controlled atmosphere furnaces, oxygen-free to prevent oxidation, to 780 to 850 degrees Celsius, 1,436 to 1,562 degrees Fahrenheit. Below copper's melting point, 1,085 degrees Celsius, but sufficient for atomic diffusion to bond particles. 5. Cooling, gradual cooling to prevent cracking. 6. Sizing, sometimes repressed for dimensional precision. 7. Oil impregnation. Placed in vacuum chamber, air evacuated, chamber flooded with SAE-30 oil. Atmospheric pressure restored to force oil into pores. Result: bearings with approximately 25 to 30% porosity by volume, completely saturated with oil. Operating principle: the microscopic interconnected channels retained oil through capillary action, but released it when heat and friction reduced oil viscosity and caused slight metal expansion. When a shaft rotates in an oilite bearing, friction generates heat. Heat decreases oil viscosity, becomes more fluid. Metal expands microscopically, pushing oil toward the surface. Oil migrates to the bearing shaft interface. When rotation ceases and the bearing cools, capillary action draws oil back into the pores. The bearing appears externally dry, but remains internally oil-saturated. This cycle could repeat thousands of times over years without the bearing depleting its oil supply. Post-war applications. When World War II concluded, oilite bearings transitioned seamlessly from military to civilian applications because civilian production had never ceased. By the 1950s, oilite bearings had become standard components in automobiles. Virtually every American car incorporated them in multiple locations. Home appliances, washing machines, vacuum cleaners, fans, anywhere small motors required bearings. Post-war expansion and evolution. Industrial equipment, factory machinery, pumps, conveyor systems, office equipment, typewriters, calculators, early computing machines, toys, electric trains, remote control vehicles. Essentially any application requiring small bearings. The Amplex Oilite division maintained its growth trajectory. In 1961, a second manufacturing facility opened in Trenton, Michigan. In 1965, sales reached unprecedented levels, 24% above 1964 figures, and the division introduced aluminum-based oilite bearings for specialized applications. By 1996, the business had transitioned through several ownership changes. Sintered Metals Incorporated acquired it, then was subsequently purchased by GKN plc. In 1997, GKN became the world's largest powder metal component manufacturer, with oilite bearings remaining a flagship product line. Modern era. As of 2024, oilite bearings are manufactured by Beamer Precision Inc. in Pennsylvania, which owns the registered trademark. The company continues production using processes fundamentally identical to William Sherwood's 1929 patents. In 2027, oilite bearings will mark their centennial. From Carl Breer's 1927 insight to a product still manufactured and distributed globally. This longevity is extraordinary. Most 1920s technologies have become obsolete, superseded by superior modern alternatives. Yet oilite remains competitive because the fundamental physics are unchanged. Porous metal saturated with oil continues to be one of the most effective self-lubricating bearing solutions available. Contemporary applications. Modern uses include automotive, still employed in specific locations where access is restricted or maintenance is impractical. Aerospace, Formula One vehicles, military aircraft. Industrial robotics, actuators and joints requiring maintenance-free operation medical devices. Equipment requiring non-contaminating lubrication. Consumer products, countless applications where reliability is critical. Material developments variants have evolved beyond the original bronze formulation. Superoilite, iron-based sintered bearing, harder and stronger than bronze, rated for higher loads but lower speeds. Plus, standard bronze impregnated with oil, plus PTFE particles, reducing friction by approximately 17%. Aluminum oilite, lightweight bearings for aerospace applications. However, the original bronze tin composition remains most widely used, designated as ASTM B438-95, A Grade 1 Type 2, and SAE 841 in industry standards. Historical significance. In 1927, Carl Breer confronted a straightforward problem, a slipping clutch caused by oil contaminating an inaccessible bearing. His solution, a metallic sponge saturated with oil, seemed preposterous. General Motors had attempted and failed. Conventional wisdom declared it impossible. But William Sherwood and Bill Calkins demonstrated its viability. By 1930, they had developed bearings that maintained their own internal oil supply, releasing it only when friction heated during operation. Timeline of impact. By 1932, oilite bearings appeared in production automobiles. By 1935, Amplex operated an extensive factory producing millions annually. By 1940, when American tanks began overheating during desert training, oilite was positioned to address an unanticipated problem. The wartime impact was substantial. Sherman tanks, P-47 fighters, Spitfires, and naval vessels all incorporated oilite bearings in applications where conventional bearings failed. The technology maintained armor mobility, kept aircraft airborne, and ensured ships remained operational in conditions that destroyed traditional lubrication systems. Peacetime legacy. The civilian contribution was equally significant. Billions of oilite bearings, manufactured over 9 decades, have reduced maintenance costs, enhanced reliability, enabled products that would have been impractical with conventional bearings requiring constant servicing. Conclusion today, nearly a century after Carl Breer questioned whether metal could retain oil like a sponge, the answer remains affirmative. The oilite bearing, porous bronze saturated with lubricant through vacuum pressure, represents one of the most elegant engineering solutions ever conceived. Simple in concept, metal with microscopic pores filled with oil. Sophisticated in execution, precise powder metallurgy, controlled sintering, vacuum impregnation, effective in application, 97 years of continuous production, billions of bearings manufactured, applications ranging from clutches to spacecraft. When American tank bearings failed in 1940, Chrysler had developed sponge metal that self-lubricated. That self-lubricating bronze, invented to remedy a slipping clutch, ultimately contributed to winning a world war and established an industry that continues thriving today. This exemplifies the power of solving a single problem well. The solution discovers 1,000 applications never originally imagined.